you hold your leaf at an angle, though, you'll get some sunlight, and then some of the sunlight you're going to miss. The interesting thing comes then when we think about plants and how they might shift the angle at which their leaves are held over the course of a season, or if they grow in different locations, okay? Just from, if everything was equal, all plants would hold their leaves like this all the time because that would give them the most light, but they don't. And so that's the interesting question then, is like, why don't all plants hold their leaves perpendicular to the ground in the incoming sunlight? So why don't they?
Burn them up.
Right. They're having to balance incoming light energy for photosynthesis versus temperature regulation and moisture loss. And so even though what's best for photosynthesis might be to be flat onto the sun, that's not what's best for you overall. And so holding at an angle then gets you some sunlight. It also helps you, as we'll talk about next week, with temperature regulation and water loss.
Where does that hummingbirds?
Yeah, that's what I'm here for. Yeah.
They'll burn them up.
That's what I'm here for. And stop me if you're like, no, that's not what I was thinking of at all. Because sometimes I'll take that student idea and I slot it into like what I need to tell you. And that's not what you're thinking at all. Happens more in environmental studies when they say something and I'm like, oh, that sounds like this, and I'm going to say this, and then the student's just like, no. Okay, tell me what you're thinking. Why else would you hold a leaf at an angle rather than perpendicular?
Blocking your other leaves.
Good. If you have one that's flat, why grow more leaves underneath it? Okay. If everybody's angled, you can put out more leaves and expect to get more stuff. Why else?
Don't angled leaves help like direct rainwater with roots?
Good. Yeah. In high precipitation environments, you may not want to have a leaf that's perpendicular. You might want to have a slanted leaf so that water is funneled where you want it to go. This is really true, again, in tropical rainforests. You see all these leaves and you have these stem structures that hold water around the stem and collect water. That's for the plant, and then other organisms take advantage of it. What we see in cold environments is that, again, a conifer leaf is really small, these little needles. And they're balancing photosynthesis versus shedding snow and ice. They're balancing photosynthesis with losing heat through a big leaf, okay? And so there's always going to be this trade-off in adaptation. What's best under idealized conditions is best under idealized conditions. That's not what happens in the world, okay? There's always other pressures. So conifer leaves and so evergreen trees, they have these really thin little needles, and they hold them at an angle usually. They're getting some photosynthesis, but they're also gaining the ability to shed snow and ice, and they're gaining the ability to retain heat. They have a ton of little needles to make up for the lost photosynthesis that you would get with a perpendicular leaf and a big broad leaf. Think about this also in terms of that when we have a big ice storm here in our region and before the leaves have fallen, kind of like we did last fall, or was it this? It was last fall, it wasn't this spring. We get a big ice storm, the ice cakes on those big flat leaves and it breaks branches because these leaves are not designed to shed that type of precipitation because it doesn't happen as often. There's less of an evolutionary pressure to get small and thin. Why else would you want to have an angled leaf? Right. more important one about why angled leaves are common. It has to do with, think about solar radiation and how it hits the earth.
Is it so that the plant receives different amounts of sunlight?
Yeah. The angle of incoming solar radiation is only like straight down from the sun at the equator. Okay? The angle at which the incoming solar radiation varies over the course of the day. We'll see some plants that actually move their leaves during the day in order to keep them full on to the sun. The angle of incoming solar radiation varies with season, as we're in different orientations to the sun. The angle of incoming solar radiation varies with latitude, with where you are on the globe. Okay? So angled leaves are also adaptive, essentially to the angle of the solar radiation. At the equator, you want a perpendicular leaf because the solar radiation is coming straight down at you. When you get into our latitude, and definitely at the poles, the angle of incoming solar radiation is quite steep. And so if you have a perpendicular leaf, they're actually not the same thing. Different seasons, you might want to be more full on or change as your angle to the sun and changes. You want your leaf angle to be adaptive or to be able to be flexible. Okay. So angled leaves actually, even though they seem like the bad choice in terms of an idealized world, that happens so rarely that angled leaves are really, really common for a whole variety of reasons. Kind of cool. I think the next thing I want to ask you about is kind of how angles of leaves affect other plants. Okay, so we can think about your angle of leaf from the plant's own perspective. Do I want it perpendicular angled? How angled do I want it? Do I want this to be fixed? Do I want to be able to move it? But then the angle of leaves above a plant can also affect that particular plant's growth. So I have a question here from the end of chapter 4. We have two areas that have the same leaf area index. The density of leaves is the same. In one forest, the plants in that particular region have horizontal leaves, perpendicular. In the other forest, most of the leaves above are angled like this. At noon in these two forests, how does light availability vary at the forest floor? Which forest floor at noon, summertime, is going to have the most light at the forest floor?
The angled leaves?
Right, the angled leaves. Okay, you're going to intercept less. More light is going to make it to the forest floor. How about at mid-morning instead of noon?
Maybe the perpendicular since the sun's not directly overhead.
Yeah. Now the situation changes because the angle of incoming sunlight has changed. More is being intercepted by these guys. Their shadow underneath is relatively bigger than the perpendicular. So again, the quantity of incoming light can vary time of day, leaf angle, number of leaves that are out there, the actual area and density of the leaves themselves. It's kind of like, oh. Now you get an appreciation, hopefully, of why we measure light levels as one of these basic foundational environmental conditions. Because it varies on such a kind of dynamic scale. If you're going out into an environment and you're measuring light levels, one of the things that's really common is to write down the time of day, to make a note of weather conditions, so that you know what might be affecting the quantity and quality of light that you're actually measuring. When you go into a laboratory environment and you want to grow different types of plants, you have to be aware of their normal conditions for quantity of light and for quality of light. And sometimes it's easy to give plants, as you're growing them in the lab, too much light, and they won't grow as they normally have, or they'll show kind of crazy physical plasticity that you don't see in the field. because you haven't got the conditions quite right. Okay, cool. All right, that's my spiel for light. Okay. Where it's one of these, again, foundational principles that determines what plants can grow where. They must have access to light. When we talk about autotroph adaptations, we'll talk about different ways in which plants, other than leaf angle, can adapt to light. And again, some of these different things that they have to balance when they're thinking about access to light. Again, we tend to think about in terms of plants, the more light you have, the better you're going to do. But that's only true for photosynthesis. And photosynthesis isn't the only thing that a plant is doing. Okay. We haven't talked at all about heterotroph adaptations, about light levels in animal organisms, but we'll get a chance to talk to them. Okay, all right. So the other thing that's super important in a terrestrial ecosystem is the soil, and we talked about this in class on Friday, kind of before we got going on our different measurements about soil. We know that temperature and precipitation determine what plants can grow where. We know that that's the basis of climate. But there has to be soil there for these major biome determining types of vegetation to be present. And so then the soil becomes the conduit for water. The soil becomes the conduit for nutrients for those autotrophs to grow. The soil is also a habitat for a whole bunch of different organisms, heterotrophs, decomposers most prominent among them, that also live there. Okay. Your textbook kind of goes to great lengths to make the point that soil is hard to define. Like I said, soil to me has this organic biological content to it. It has had some interaction with biology to be soil versus rock or dirt, which we think of as just inert mineral material. Even a soil scientist would have trouble really laying out a hardcore definition of soil because there's so many variables that are possible. And depending on your perspective, it's soil or it's rock. Where do you make the boundary between those two? Depends on what it is you're asking in terms of your question. And so it might vary just a little bit depending upon the research system, if it's soil or not, where are the boundaries of this definition. But in general, we can think of soil as that combination of physical weathering of rock plus interactions with living organisms. It has that biological component to it. Soil is important, again, because it's the site of water infiltration. It's how we get fresh water to most types of plants. It's the site of a ton of terrestrial decomposition. That's where this takes place. And as a result of that decomposition and water infiltration, a ton of our nutrient cycling happens in the soil. That's where we take the matter that's stored in living organisms and return it into those inorganic nitrogen, phosphorus, sulfur, magnesium, iron compounds that we need in various amounts of soil. All right, this is a nice picture of one of the parks in Canada where you can see that some of the soil has been kind of brought to the surface, either from some type of erosion process or forest fire. It looks like probably in this location that has kind of taken out the dominant vegetation and left the bare soil then to be repopulated by plants in the region. Again, keeping in mind that soil is this abiotic thing. It's this mineral content that we can measure pH of and permeability and temperature of, nutrient content, just like we did on Friday. Then it has this huge biotic component. Okay, and we'll do a little bit with soil invertebrates, not this week, but next week in lab. And there's a ton of microorganisms that live in soil that are really interesting and exciting. And there's a ton of fungi that live in soil too. Okay, it's kind of fun to think about how we make soil, just so you can put this in perspective of this, really important substrate for terrestrial ecosystems. Where does it come from? So there are two basic processes that turn rock into soil. Okay, and they are what we would consider weathering processes. We have to break down the hard mineral limestone or granite or sandstone, and we have to turn it into soil. So essentially what's happening in any of these processes, we're taking big pieces of minerals and we're making them smaller pieces of those minerals. And we're adding some stuff around it. And the way that we break down big pieces into small pieces is either through mechanical or chemical weathering. And in mechanical weathering, we're going to have the wind, we're going to have water rubbing over something, we're going to have temperature changes, expanding and contracting big particles of rock and breaking them apart. Definitely, you can imagine if the wind blows hard, we're going to pick up pieces of rock, we're going to rub those rock pieces together, they're going to break into smaller pieces. Same thing with water. Lots of water rushing over a surface, high water movement tends to lead to lots of erosion and weathering because we're rubbing away at the surface of that mineral, we're dissolving it. You can see then that the pH of that water will have an effect on the rate of weathering. Okay. Neutral does less weathering than a very basic or an acidic pH of water, which tends to help with dissolution of minerals. The temperature one, again, is one that I think is really interesting in that in places where you have big temperature shifts over the course of the year in the mid and the high latitudes, you're going to have expansion when these things warm up, and then you're going to have contraction when they shrink down. If there's water that gets in between cracks in a mineral, as that water expands and contracts, it's going to help burst apart that rock particle into something small. So temperature plays a bigger role in soil formation at mid and high latitudes where temperature varies more than at the equator where it's relatively stable.
Then we get potholes.
Yeah, that's the biggest thing that happens in our region. And again, you see them appear in springtime. When you have this expansion of the water that's gotten into the cracks over the winter time, and then as it warms up and the ice melts, it like pops it. And then you have people driving over it, you have this frictional process that erodes away the surface. Super annoying.
You say mechanical, like water, that's just like erosion kind of in a way, and then chemicals, just like a certain element or certain atom interacting with the water fundamentally changes.
Exactly.
Okay.
And so in the chemical sense, you can think that you're going to have organisms, you're going to have water, you're going to have oxygen in the atmosphere, you're going to have different minerals that are present in the soil substrate that are interacting with those mineral compounds and breaking them down into smaller particles. And so again, you can think of the water in terms of water velocity as rubbing stuff away. Water pH is the chemical side of water weathering. Biology can do either one. Biological organisms in terms of roots growing into rocks can be mechanical weathering and breakdown, the splitting of rocks. You can have compaction of soil particles due to the packing in of organisms as they build their burrows and kind of pack in around them. You can also have biology, particularly decomposition, that's going to be altering the chemistry of the soil. And as you alter the chemistry and the nutrient content of the soil, you can introduce chemical weathering as well. Okay, you guys are all right. There are 5 general things that determine what soil, in terms of these soil orders that we worked with just a little bit on Friday, what soil occurs where. So we talked about, what biome do we find where? That's due to the climate. It's underlined by the type of soil that's there. What soil do we find in each location is due to climate, the temperature and precipitation. It's due to biology, the organisms that have lived there and that are living there now. The type of soil you find at a location has a ton to do with what we call parent material, with the rock that was there to start with. Okay, you get very different soil if you start with limestone, sandstone, or granite, because you start with different base minerals. Topography, kind of the steepness of the slope, also plays a role in soil formation and what soil you find where, and time. Those are the 5 factors that really affect what soil you're going to find at any given location. Definitely in a desert soil where you have lots of evaporation, you're going to have a very different soil structure than in a temperate location. Definitely, even at a temperate location, places where you have trees versus grass, you're going to have a different type of soil that forms. If it's underlined by a different type of bedrock, you're going to have a different soil which is capable of forming on top. Tropical soils we'll talk about are pretty interesting. They're kind of the opposite of the desert. In the desert, you have all this evaporation and this depositing then of salts and ions and minerals in the soil. The opposite happens in tropical locations where you have lots of precipitation. Everything leaches out and runs off from the soil rather than being retained in it. And so climate, just in precipitation, can affect what type of soil you had there. What you start with is based on your parent material. What's happened over time has to do with organisms and climate and the particular topography of that location. And then the soil, just like communities and organisms change over time, soil changes over time too. Okay? It's not a static for an environment. But the time scale of change is really long. Okay? For most of our experiments, we can think of soil as pretty constant, but on geologic timescales, on evolutionary timescales, the soil can change. Okay, so just a little blurb about this idea of soil formation. We have 5 factors. I think one of the questions at the end of chapter 4 again asks you, what are the 5 factors that affect soil? It's climate, it's organisms, it's parent material, it's time, and it's topography. Okay, makes most sense to me to start with parent material. The underlying rocks, the bedrock source, the geologic cycles of erosion and sedimentation that lay down new layers of soil are going to make the inorganic minerals that start off soil formation. And again, when you have a limestone that you start with in places like Florida, you're going to have a higher proportion of calcium and carbonate in the soil than if you start off with a granite or a marble underlying. If you're in an environment like the Mississippi River Delta, where you're laying down a bunch of sediment, you're going to have a different type of soil that forms than in a place like the beach, where you have a bunch of erosion that's taking away sediment. Okay, so the parent material to start with will affect what type of soil you get. Okay. The next thing that it makes sense for me to think about are these biotic factors, are the organisms in the biology and how they affect the soil formation. Plants and animals can affect soil formation, and they can be little ones or they can be big organisms. They can be microscopic and macroscopic. In general, the more plants you have, the more sedimentation you'll have. The higher the buildup of organic matter you'll have in the soil. But that's layered onto starting material and temperature and precipitation. The more chances that you have for burrowing organisms in the soil, the greater aeration of the soil you'll have. Each of those little burrows is a place for oxygen to get into the soil. That can affect decomposition rates, which affects nutrient cycling, which affects ionic balances and the type of weathering that's going to happen in that soil. Definitely, the bigger, the thicker the plant roots, you're going to have different soil formation processes in different horizons or depths of the soil than if you're in, again, a prairie environment where the roots aren't quite as deep. The organisms play a role. Definitely, in terms of plants, the way in which they shed their leaves and grow new leaves is going to affect soil formation. Here in the prairies and the deciduous forests, we have this huge input of organic matter that happens every fall and winter. That's not true necessarily what happens in tropical and polar ecosystems, where those plants hang on to their leaves for a lot longer. The cycling of organic matter and nutrients is very different in the soil there because of the different types of plants. Okay, the next thing, of course, is climate and the temperature, the variability of the temperature, the precipitation, not only the amount of precipitation, but the pattern of precipitation over a year will affect soil formation. In general, the more precipitation, the more variable the temperature, the faster erosion takes place. Okay, the warmer something is, the more water you have flowing around, the more weathering and erosion will take place. And again, that can be good for building soil and breaking down stuff, but it means if you have lots of precipitation, just as you're breaking down and building soil, you're also rinsing out a lot of soil ions and nutrients too that will affect the rate of soil formation in terms of the biology. Definitely, the winds that you have blowing across a different region are going to affect the ability of soil particles to sit in place or to be moved to other locations. The temperature, the precipitation, the dominant wind pattern affect what organisms grow there, and the organisms affect what soil forms there. So they're interconnected. And we can talk about generalities like warmer, wetter means more erosion, but then the biology is layered on top of that too, and the parent-material plays a role. Okay. In terms of climate and precipitation and temperature, we can talk about leaching, which is the movement of solids through the soil. It's where, again, you have a lot of rainfall is going to leach out stuff. That movement of water is going to dissolve and blow things out of the soil, whether that's out into another ecosystem, out into an aquatic ecosystem, or out into a deeper horizon of the soil. Those are all possible with leaching. In general, as I mentioned, hotter means everything goes faster. Okay. Weathering goes faster, decomposition goes faster, growth of organisms goes faster. Those all have different pushes and pulls on soil formation.
Then doesn't, if it gets too hot, doesn't it slow everything down, like for like the desert and stuff?
It can, and again, but there's also that precipitation aspect to it. And so in general, hotter is faster, but if you don't have the water to kind of keep the system running, it will slow down. And that's where you get like too hot, is you get too hot for the biology to work. You get too hot for precipitation too. Okay. The fourth factor is topography, the contour of the land. In general, again, the steeper the slope, the faster the wind goes, the faster the water goes, the faster erosion goes. And the more erosion you have, the harder it is for a soil to build up. Okay, so high on the mountainside where it's very steep, all the soil runs off and it gets deposited in the valley below. Okay. So in places where it's flatter, you're gonna have soil build up. You're gonna have soil deposited rather than removed away. And again, this can play across big landscapes, or it can be in just a little region like we have here on campus. The upper areas we're rinsing stuff away and it's collecting and building up down in the lower flatter zones.
Did you say the steeper the land, the faster wind and the faster the water?
Yes, in general. We like rules, and then we break them all the time. But in general, the erosion, the formation of soil will be faster in these locations, but that's not where the soil ends up. It gets rinsed away. Okay, steeper, more erosion, more runoff, less accumulation. The steeper it is, the more erosion you get. More runoff of water, the less soil accumulation. And again, the less soil you have, the harder it is for plants to grow, the harder it is to stabilize soil and get it to build up. Okay. And the last thing here is time. If you really want to build a soil, it's not an overnight process. It's not even a yearly process. In order to build up a soil and what we consider soil, we're talking about 2,000 to 20,000 years. We're talking about many cycles of expansion and contraction, many wet and dry seasons, many life cycles of many different organisms in order to produce the soil that's in place. So once you have it, then you can start to layer on top of it different types of organisms in different processes. Okay. All right, so this gives us our 12 different types of soil orders. Soil is classified just like organisms based on its texture, its color, its nutrient content, its mineral content in terms of parent material. Definitely what we did in terms of class on Friday was we kind of looked at the color and the grittiness, the sand versus silt versus clay texture of the soil, and we tried to pop them in here. Soil scientists get really excited about this. And we see again that certain types of soils will occur at different latitudes because of temperature precipitation processes that produce that particular type of soil. Definitely in our region, we have lots of these types of his soils, and I think the other one that we saw a lot of was like this guy and maybe a little bit of this one. Those are common in these mid-latitude regions where we have a high organic input and we have lots of biology that's kind of dominating these processes. Okay, am I going to ask you to identify soil orders? No. Okay, this is cool and all, but you'll always have the access to this chart. Okay, and I'd rather that you were really understanding of how we get to these soil orders rather than the defining little features of each little soil order. Okay. There are a few processes that are common in soils that have to do with nutrient distribution and rainfall that I do think are a little bit interesting to think about. And again, it's kind of that the process here is much more interesting and intriguing, I think, than the end product of the particular soil order. So there are 5 of these processes that help us build different soils. And we have these 5 factors that produce the soil, and then these are the processes that are somewhat involved in those 5 factors. So the first one is lateralization, and this is the movement of large quantities of water that causes heavy leaching and rapid weathering of the soil. And lots of lateralization often leads to an acidic soil because we're changing kind of the ion content. Most soil particles are pretty negatively charged. And so as water and different ions move through them at high volumes, those negative soil particles will attract a bunch of cations. And a lot of hydrogen ions then can make a particular soil more acidic due to that process. Lateralization is really common in our humid tropical and subtropical biomes where we have lots of precipitation. It's going to be leaching nutrients and ions from the soil. And the soil orders that result from loss of lateralization are things like our oxasols and our utasols. I'm not even very good at pronouncing these guys. Okay. So lateralization is a movement of a large quantity of water that leaches out minerals and nutrients from the soil. It tends to be the process of soil formation that dominates in our high precipitation tropical and subtropical environments. Yeah.
So does it make soil more acidic? Is that what you're saying?
It does. Like over the long term, it's going to take out and move through a whole bunch of ions, and the negative soil particles, the negative soil mineral itself, is going to latch onto a whole bunch of positive ions. And a bunch of that tends to be hydrogen ions. More hydrogen ion, lower pH, more acidic pH is what it comes out measuring.
So that's bad for plants, right?
It can be. We see that the plants then that grow in these types of soils are adapted for acidic conditions. They do fine here because other plants will be excluded because it's too acidic. But the plants that do grow there are adapted for those conditions.
The plants in tropical.
That's again another one reason why if you take a plant from a tropical environment and you try to plop it down in Ohio, it's one reason why it might not do well because our soil pH is different. I think you can think of lots of reasons why it might not. Okay, the next important soil process is calcification. And calcification is where we have high rates of evaporation and plant water uptake that actually draw salts up into the soil from the bedrock below. Okay. Calcification, it definitely, makes you think of laying down layers of calcium. In this case, it's like calcium carbonate in addition to other things. And you get this layering of kind of white salts that form in the mid layers of your soil horizon. And that's calcification. This is when you have evaporation and plant uptake of moisture that draws the moisture and with it these ions up from below. Okay. And you get this deposition of these alkaline salts in kind of what we're going to call the B horizon of the soil profile. It's typical of things like mull soils, which have a bunch of organic content at the top. And then as you get down into the lower layers, you get these interesting kind of lines of salt deposition before you get into the more mineral layers of your soil. We occasionally will see calcification in our region in agricultural fields. So where you have lots of plant growth that are pulling up moisture and ions from below, you can have this kind of upward movement of stuff through soil corals.
So which one on that picture is the D horizon? Is it the top layer or the bottom layer?
So this is O, the organic stuff. This is A, right underneath it, and this is B.
Gotcha.
Okay, and this is the calcification zone right here between A and B. It's like O for the organic horizon, and then it's like A, B, and C. Not super complicated. All right. Okay. The third process that's important for soil formation is salinization, and it's very similar to calcification. It's just that we're going to deposit ions and salts at the surface of the soil because evaporation is so high, rather than kind of down in the soil holes. So in salinization, we have evaporation and plant water uptake are much, much greater than precipitation. And as a result, we see salts that actually accumulate at the surface of the soil. And so this happens in deserts, places where you have lots of sea spray that throws up salt water, and then the salt water evaporates and it leaves the salt behind. You get this kind of crusty, almost crystalline formation of salts right at the surface of the soil. It happens in brine pools, like at the edge of the salt lake. You get this formation of salt. It happens at the edge of places like the Dead Sea and the Red Sea. We have really high evaporation that leaves behind salts at the surface. Salinization is normal in those types of ecosystems. What we're seeing today is a lot of salinization in drier agricultural regions. And that as we pump in irrigation water, as that irrigation water evaporates and is used by plants, it leaves behind the salts. And we're adding constantly more water and more salts to the soil than the natural process for kind of weathering and burial of those salts. And so over time, the salts become more saline. They build up these ions that in high concentration can actually be bad for agriculture in the long term.
So just salt in the earth over time?
Yeah, I mean, like literally.
That's it.
Yeah, you're right. Oh, bummer. It's something that led, along with poor agricultural practices, to the Dust Bowl scenario that happened in the early 1900s in the kind of panhandle of Texas, Oklahoma, Kansas region. They not only had kind of a drought situation, they had poor agricultural practices where they lost a bunch of topsoil, they lost a bunch of plants, and at the same time they were experiencing salinization. And then it just made it really hard to grow plants. And then the wind came along and threw all the soil up into the air and got these huge dust storms. We have totally changed how we grow plants in that region of the United States so that we can avoid dust bowl scenarios in the future. The problem is it's starting to happen in other places as climate changes. And that's something that we have to adapt to if we want to continue to be agriculturally productive at the same rate we are today. Okay, this is an interesting one. I call it podzolization. This is where you have a really acidic soil. It's all about the parent material. The parent material has the right mineral ions in it to be very acidic in nature. And because of that, it really enhances chemical weathering. And you get the leaching of other types of minerals and ions out of the soil. And in this case, it's not necessarily due to big water flow. It has everything to do with either biology or with the parent material that gives you a really acidic soil. In this case, you often see that at the bottom of the A layer, you'll get, again, this kind of deposition of these types of leached minerals. In addition to having a very kind of acidic prone starting material, we often see that this process is very common underneath conifer forests. And so as conifers lose their needles and shed them, it tends to acidify the soil. And as a result, podzolization can be one of these dominant processes that's happening in the soil underneath places like the temperate conifer forest in Washington and Oregon state, and definitely up in the taiga kind of tundra region, and polar regions where conifers tend to dominate. You may notice that if you have a pine tree growing in your yard and it drops all these pine needles around it, there's not a lot of plants that grow underneath the pine tree. Okay? Part of that is light. There's not a lot of light down there underneath all the needles. The other big thing that happens is that it makes the soil too acidic for lots of different types of plants to grow. And so that's a competition mechanism of the evergreen tree to reduce competitors around its tree. Okay, the last kind of soil process here is glaciation. And this is where we have an accumulation of organic matter from very slow decomposition. And so glaciation is when you have really slow decomposition that lets organic matter accumulate. And this tends to happen in very wet, waterlogged soils. And in these locations, the enhanced amount of water means there's not a lot of air that gets into the soil. And if this is a relatively flat region with lots of plants growing, you'll get a whole bunch of dead organic plant matter that just kind of sits there and builds up over time in the soil. This is your classic peat bog, where you have this ever increasing amount of organic matter and it just sits there. And that makes a very specific type of soil that's really different than other places. So it happens in waterlogged soils, either high rainfall and poor drainage conditions. You tend to get this blue, gray, black color that looks very clay-like in terms of the soil. And again, it tends to dominate around stream beds and in swamps and bogs. And again, it has a really different mineral content. It's going to support really different types of plants than in other locations. Okay, a question there. Okay, so we have a wet tropical region. Which of those 5 soil forming processes we just talked about, the glaciation, the podzolization, salinization, calcification, what was the first one? Laterization. Which of those 5 is going to be the dominant soil forming process in a wet tropical region? Which of those 5 Asian ones?
Can you repeat them again? You said lateralization, calcification, salinization, glaciation, then
It's podzolation. I'm going to go with. I've been watching Lost in Dark Crystal. And have those little pod things. Which of those 5 do you think is going to dominate in a wet tropical region? I think so too. I think laterization, where you have this high volume of water from the precipitation, is going to be the dominant process there. Definitely the calcification and the salinization aren't going to be it, because we have much more precipitation than we have uptake and evaporation. It depends a little bit on topography and the biology that's there. If I would say like glaciation might play a role, this water logging, slow decomposition stuff. Okay. And then we see just really typical in tropical rainforest soils, this type of profile. So we're looking at like a stream bank in the tropical rainforest versus in Ohio. And you can see the soils are like totally different, okay? Why is there so much less organic matter in the tropical rainforest versus Ohio?
calcification.
No. Yeah, ground leaching. This idea of laterization, that is just rinsing out all of the nutrients, okay? The really rapid loss of nutrients means that tropical rainforest soils are actually pretty nutrient poor, especially compared to temperate forests or prairie forests like we have here. Okay, so how does this process of laterization then influence the availability of nutrients for plant roots in the rainforest versus Ohio? So what does a lot of lateralization mean for nutrient availability for plants in these two environments? Where? It's reduced in the rainforest, okay? There's less nutrients held in the rainforest soil because it gets lost really rapidly to precipitation and the bleaching. It also means that if you're a plant that lives in the rainforest, you're adapted to snap up any nutrient that appears in the soil, okay? You're much more adapted for nutrient absorption than in a place like Ohio where you know nutrients are going to be present all the time. What does that mean for farming in the rainforest versus Ohio?
A lot harder.
Where?
The rainforest.
It's a lot harder in the rainforest. Rainforest soils are not built, they're not formed to hold and hang on to nutrients. It means that if we clear rainforest for the purpose of farming, that soil is only productive for 3 to 10 years. And then you have to clear a new space to grow crops because you have depleted the area that you've been in. What do you think?
Well, I'm just thinking of a needs, but
Yeah,
like,
I want you to think about that. That's why I would bring it up, okay? We talk about clearing the rainforest, and the fires that we have in the rainforest in the Amazon basin right now are a result of farmers trying to clear out the trees to grow crops.
so it doesn't really benefit them.
No, it helps them in the short term, not going to be helpful for them in the long term. And that's why they have to continually burn more forest, and we have this ever-increasing encroachment and deforestation in these tropical rainforests. Because what people are trying to do there does not fit with the ecosystem and the conditions and resources that are there. It's really easy for us to shake our heads and be like, dude, science, okay? Science says no, okay?
Everywhere, though.
But it's everywhere. And we're not there trying to feed our families, okay? If I lived in the rainforest, I'd probably be out there hunting rainforest animals and burning down trees, okay? That's to me the really interesting part of ecology is when we can take science and understand why something is happening, and then we try to layer it onto human behavior. And it's like, yeah, and so like, how do we do that? How do we better communicate science? How do we better use science and our ecological understanding to better manage our ecosystems? Okay. To me, that's the really cool part. Okay, we're at 1:40. It's the end of today. We'll pick up here talking just a little bit about soil and agriculture and soil horizons on Thursday, and then we're going to move into chapter 5. We're going to start on evolution. Is there anybody, or I should say, if you